Welcome to ACE family. I am Dr. Satish Kumar, professor in ECE. Okay, today in this live session, we will be discussing few topics of one of the device by name PN diode. First of all, electronic devices and circuits is one of the base subjects which is definitely required for an engineering graduate in ECE department and also useful for electrical and IoT department students. In this subject, construction, operation, volt ampere characteristics of multiple devices will be discussed. We now comment on PN junction diode. PN junction diode is one of the base device. Why? Because all electronic devices in this world are made up of PN diode. Understanding the operation of PN diode is very much required. Why? Because once you understand this device, understanding all other devices, Zener diode, tunnel diode, BJT, JFET, MOSFET, etc. will become easy. Now, we'll look at different topics of this PN diode. Open circuit, forward bias, reverse bias, current components, volt ampere characteristics, diode resistances, equivalent circuits. Load line analysis, transition capacitance, diffusion capacitance, switching times, applications and numericals. These topics have been collected from different syllabus of different universities. Okay. First of all, I'll give you some basics of this PN diode and then move on to the first topic, that is derivation of equation for transition capacitance. An intrinsic semiconductor bar made up of silicon or germanium is considered having a length L and cross-sectional area A. Into it, at one side, donor impurities are added, making it N-type. Donor means pentavalent atoms. At the other side, acceptor impurities are added, making it P-type. Acceptor means trivalent atoms. Later on, from either ends, two metallic contacts are pulled out. This central dotted line is an imaginary line which is drawn for explanation purpose, just to separate the P and N sides. This notation can be observed here. It is shown here. It is a donor atom with excess electron, which is basically neutral. If this donor atom loses an electron, it becomes a positive ion, as shown here. This dot represents excess electron. This is acceptor atom with excess hole, which is basically neutral. After accepting an electron, it becomes a negatively charged ion, as shown here. This small circle represents a hole. Now, if you look at this diagram, in N side, we have more number of electrons, majority carriers, and less number of holes, called minority carriers. In P side, we have more number of holes, called majority carriers, less number of electrons, called minority carriers. According to this diffusion concept, whenever there is a difference in concentration, diffusion of charge carriers should occur from higher to lower concentrated area. Ideally, until uniform carrier concentration is achieved. Hence, electrons of n side diffuse to p and recombine with hole. Hole of p side diffuse to n and recombine with electron. During electron-hole pair recombination, we observe that positive and negative ions will get created. These are neutral donor atoms. They have lost electron and hence become positively charged ions. These are neutral acceptor atoms. After they accept electrons, they become negatively charged ions. It can be observed that due to electron-hole pair recombination, at the center positive and negative ions got created which oppose further diffusion. And the central positive and negative ions which are opposing further diffusion is given the name barrier. W is called width of barrier. So this diagram is without barrier and this diagram is with barrier. Any diode in the world, any practical diode in the world is of the type with barrier. This central barrier is given multiple names. It is called as depletion region. It can be observed that in this central area, we do not have electrons or holes which can support current and hence given the name depleted region. Depleted in English means not available. Electrons and holes which can support current are not available in this area and hence called depletion. This area is having neutral atoms and this area is having neutral atoms. But the central part is having positive and negative ions. So this is the only region where charges are existing and hence given the name space charge region. Now, this is also given the name transition region. Why? Because it is separating two neutral areas and it is given one more name called junction. So barrier, depletion region, space charge region, transition region or junction all mean the same. Now, across these positive and negative ions, internally electric flux lines will get developed and hence an electric field E0 will get induced or a voltage V0 will get induced, called as open circuited contact potential, open circuited electric field. Remember that this V0 and E0 are induced. Induced means internally generated. Applied means externally initiated or externally triggered. Now we move on to the circuit symbol. A circuit symbol should give two services. Number one, it should identify the number of terminals. Number two, it should identify the names of terminals. By looking at this circuit symbol, we can say that it is having two terminals. This vertical line represents N, triangular piece represents P. This arrow shows direction of flow of current when the diode is forward biased. When the diode is forward biased, current goes from P to N and hence the arrow is pointing from P to N. Now, before the existence of this solid state PN diode, we had something called as vacuum diode. It is a glass structure, internally vacuum, having two electrodes by name anode and cathode. This was the original version of PN diode. This is vacuum version. This is a solid state device. So to remember the first ever vacuum diode, this device is said to have two electrodes. Di means two. OD is a part of electrode and hence given the name diode. We have one p-type material, one n-type material and hence called PN diode. Just now we stated that at the center a junction is getting created and hence it is given the name PN junction diode. Thus it is called PN junction diode or PN diode or simply diode. Now we move on to the first topic, that is transition capacitance equations derivation. Remember students that in live chat you can post your doubts. I will now and then look at the live chat and then respond to your queries. I am considering a PN diode under reverse bias condition. A diode is stated to be reverse biased if the voltage given to N side is more positive when compared to P side. Now, if you can observe here, it is written as P plus. P plus means heavily doped. That is, P side is doped more than N side. That is, acceptor concentration is greater than, very much greater than donor concentration in this diode. Such type of diode is considered under reverse bias condition. Now, this notation was already explained to you earlier. See, W is width of depletion region under open circuit condition. In this area, some electrons were existing with the donor atoms. All of them were pulled away to the right side by the positive supply of reverse bias. In this area, holes were existing with acceptor atoms. They are pulled to the left side due to the negative supply. And hence, more number of positive and negative ions will get created. And hence, width of depletion region increases in a reverse bias diode compared to open circuit condition. WR is width of depletion region in reverse bias case. W is width of depletion region in open circuit condition. Assume reverse bias is varied. Assume this reverse bias is either increased or decreased. Then width of depletion region will either increase or decrease. As reverse bias changes, width of depletion region changes and hence positive and negative ions existing inside depletion region will also vary. And hence a non-zero value of dq by dV is exhibited, which is by definition capacitance. Non-zero value means as voltage varies, that is, as reverse voltage varies, charge will vary. Charge means charges of depletion region will vary. And hence it is given multiple names: depletion region capacitance, space charge region capacitance, transition region capacitance, and barrier capacitance. In the word transition, alphabet T is considered. In the word capacitance, alphabet C is considered, and hence put together it is given the name CT, transition capacitance. I am now considering a step junction diode for explanation purpose. First of all, let us see as what is the meaning of step junction diode. In N side, throughout the length, assume same number of donor atoms are added per cubic volume. And in P side, assume same number of acceptor atoms are added per cubic volume. And exactly at the center, acceptor concentration changes to donor concentration. Such type of construction is called step junction diode. There is one more type called as linear junction diode, but as on now, I am considering a step junction diode for explanation purpose. As I said earlier, I am taking a P plus N diode, that is acceptor concentration very much greater than donor concentration under reverse bias condition. To N side positive supply, to P side negative supply is given, so the diode is reverse biased. Now, Wn is width of depletion region in N side. Wp is width of depletion region in P side. Assume the central point is origin. To the left side, distance is negative, to the right side, distance is positive. We know that depletion region will exist both in N and P sides. But due to difference in doping, Wn will be very much greater than Wp, because depletion region penetrates more into lightly doped side. Out of P plus and N, N is lightly doped, and hence Wn is very much greater than Wp. Based on this, W, width of depletion region, can be expressed as Wn minus of minus Wp, and hence it comes out as Wn plus Wp. If you can neglect Wp compared to Wn, then W comes out as approximately Wn. According to Poisson's equation, d square V by dx square is minus rho by epsilon, where rho is charge density and epsilon is permittivity. Now, this rho I am replacing by some equivalent. Let us see how it has been formed. The unit for rho charge density is Coulomb per centimeter cube. Coulomb per centimeter cube. Nd is donor concentration, that is number of donor atoms. Number of donor atoms added per centimeter cube. A donor atom is a pentavalent atom. It has 5 electrons in valence shell and has 1 excess electron. 4 electrons will sit in 4 covalent bonds, and there will be 1 excess electron. So number of donor atoms will be equal to number of excess electrons. Unit of Q is Coulomb per electron. If you take the product, cancel out electron, we are left with coulombs per centimeter cube. That is the unit of charge density. So now rho is charge density and Nd is donor concentration, number of donor atoms added per centimeter cube. And this figure B shows variation of charge density rho with distance. This x-axis is distance and this is the origin point. See, in N side depletion region, we have positively charged donor ions, and hence charge density will be positive. It can be observed that it is above x-axis. In P side, inside depletion region, we have negatively charged acceptor ions. So charge density should be negative. It is shown below x-axis. In this diagram, you can observe that Wn is very much greater than Wb. That is, penetration of depletion region into N side will be more than P side. Why? Because N side is lightly doped. So rho is positive in N side, rho is negative in P side. Electric field by definition is minus dV by dx. Just now we have modified Poisson's equation d square V by dx square as minus q and d by epsilon. Now this value of d square V by dx square we will substitute into this equation. See, electric field by definition is dV by dx. The dV by dx can be modified as integral of d square V by dx square. So in place of this d square V by dx square, now we will substitute this value which we got from Poisson's equation. So we get this. This integration is being done with respect to distance. If you can observe, Q charge is independent of distance. Donor concentration is number of donor atoms added per centimeter cube or per cubic volume. It is also independent of distance. Epsilon permittivity is also independent of distance. So all these are independent of this dx, integral variable. So integral dx will come out as x, and hence we get this equation. It can be observed that we are adding k1, which is an integral constant. Let us see how to find out the value of this integral constant. Before finding out that integral constant, we will look at a graph, that is figure C, which is drawn for electric field versus distance. As I said earlier, x-axis is distance and this central point is origin. Wn, hope you can recall, penetration of depletion region into N side. Wp, penetration of depletion region into P side. This is in N side, that is in P side. Now, at this point and at this point, it can be observed that depletion region comes to an end. To the right side of this, what do we have? Neutral atoms. To the left side of this, what do we have? Neutral atoms. As we know that electric field can exist only across negative or positive ions or across ions. So by the time you come to the end of depletion region, electric field should definitely become zero. That's what we observe. At Wn, electric field has become zero, and at Wp, electric field has become zero. Or to say, to the right side of Wn and to the left side of minus Wp, electric field should be zero, and it will be maximum at the center, called as E0, electric field intensity. So this figure C shows variation of electric field with distance. Now using this graph, we will try to find out the value of K1, which is an integral constant. At x is equal to Wn, which is approximately Wp, from the graph it can be observed that electric field is zero. So in this equation, electric field will become zero if x is replaced by W. If x is replaced by W. Now, see, 0 equal to q and dw by epsilon plus k1. So from this, k1 comes out as minus q and dw by epsilon. Substitute this value of k1 into this equation and simplify, then we get E equal to q and epsilon by x minus w. This is the equation for electric field intensity. For a moment of time, let me see whether any queries have been asked by students. Okay. As on now, there are no queries, so I'll continue the discussion. Contact potential V by definition is minus of integral E dx. Just now we have derived the equation for electric field as qnd by epsilon into x minus w. We'll substitute this value of electric field into this and then try to get the equation for V, voltage, contact potential. Now if you can observe at this equation, we are differentiating it with distance dx. We are differentiating it with respect to dx. Q, as I said earlier, is charge. It is constant with respect to distance. Nd, donor concentration, is also a constant. Epsilon, permittivity is also a constant. Integral x dx, as we know, is x square by 2. W is width of depletion region. Hope you know that it is also a constant. Unit of W is centimeter. Unit of X is also centimeter. But W is width of depletion region. It is a constant. It can increase or decrease if the diode is reverse biased. But it cannot vary with distance. So integral W dx will come out as integral X. Integral W into dx will come out as W into X. So qnd by epsilon is constant, pulled out. Integral x dx is x square by 2. Integral w dx is wx plus k2. This is an integral constant. Now, before finding out the value of integral constant, we look at a graph. That is figure D, the last one. It shows variation of contact potential with distance. Now, this is the equation which we have derived, in which we are supposed to find out the value of K2. Now look at this graph. This is the origin point and x-axis, as we know, is distance. At x is equal to 0, from this graph it can be observed that contact potential is also 0. So at x is equal to 0, V is equal to 0. Now substitute these values into this equation. V is 0, x is 0, and this is also 0. And hence we get 0 plus 0, 0 equal to 0 plus K2. From this it can be easily understood that K2, integral constant, is 0. So if we substitute this as 0, then we are left with V equal to minus Q and epsilon into x square by 2 minus wx. So based on this graph, we have found the value of integral constant K2 as 0, and hence this equation is rewritten here. Now, this contact potential is varying with distance. By the time you come to the end of depletion region in N side, Wn, it can be observed that contact potential has become Vg. V will be equal to Vg. We are writing here x is equal to Wn, but Wn is approximately W. And hence at x is equal to W, from this graph V comes out as Vg. Contact potential comes out as Vg. Let us see as what is the meaning of this Vg. It is called junction voltage, which is defined as V0 minus Vd, where V0 is open circuited contact potential and Vd is voltage across diode. It will be positive for forward bias and negative for reverse bias. Let us see how this Vj gets affected in forward bias and reverse bias. Suppose a diode is forward biased, then junction voltage Vj equal to V0 minus Vf, and hence junction voltage decreases by an amount of applied forward bias compared to open circuited contact potential. If you consider a reverse bias diode, Vj Vj will be equal to V0 minus of minus Vr, that is junction voltage will be greater than open circuited contact potential in a reverse bias diode, which can be easily understood. Why? Because in a reverse bias diode, width of depletion region increases. Hence, positive and negative ions of depletion region will increase, and hence contact potential increases over and above V0. In a forward bias diode, width of depletion region decreases. Positive and negative ions of depletion region decreases, and hence junction voltage will be less than V0. Assume the diode is open circuited, then the applied voltage will be 0, and hence Vj will be equal to V0. That is junction voltage equal to V0 open circuited contact potential in open circuited diode. Vj is less than V0 in forward bias case. Vj is greater than V0 in reverse bias case. That is the meaning of this Vj equal to V0 minus Vd. Now at x is equal to Wn, approximately W, just now I stated that junction voltage is given by Vg. And now we will substitute this into this equation. That is, x is replaced by W, this becomes W square by 2. Here x is replaced by W, it becomes W square, and V will be replaced by Vg. Now if we pull out the common entities, we get Vj as Q Nd W square by 2 epsilon, where Q is charge, Nd donor concentration, W width of depletion region, and epsilon is permittivity. From this it can be observed that width of depletion region is proportional to square root of junction voltage. Why? Because Q, Nd, 2, epsilon are constants. W will vary as proportional to square root of junction voltage. This is an important thing which is to be remembered. Before going to the next one, let me see whether any queries are existing. Okay. As on now, no queries are there. So I'll continue the discussion. Now, we want to find out total charge existing inside depletion region of N side. Why? Because the equation for transition capacitance is dq by dV. If you can find out Q and differentiate with respect to voltage, then we'll get the final equation for transition capacitance. Now, before finding out the total charge, let me see how this equation has been written here. See, we want to find out charge inside depletion region of N side. Now, the unit for charge, as we know, is Coulomb. The equation for Nd is number of donor atoms equation for Nd is number of donor atoms per centimeter cube. Each donor atom can give one excess electron. So this can be modified as number of electrons per centimeter cube. Fine. Now we want to find out Coulomb Q, but here we have electrons per centimeter cube. I am multiplying with A cross-sectional area of PN diode. Unit for area is centimeter square. Now we want to find out charge inside depletion region of N side. Depletion region is existing in N side up to Wn. Now this Wn is approximately W. This Wn is approximately W. Unit for W or Wn is centimeter. If we cancel out, we are left with number of electrons. Actually we want Coulomb, not number of electrons. So I am multiplying with Q. The unit of Q is Coulomb per electron. Final unit of this complete term is Coulomb, which is nothing but unit of Q. So whenever we want to write an equation, the best thing is rather than by hearting the equation, better try to write the equation based on the units. So units of left hand side and right hand side should match. So if you write in that way, there will be no need of by hearting any equation. So as I said earlier, W is approximately Wn, which is approximately W in this equation. A is area of cross section of diode. Now transition capacitance by definition is dq by dV. If you can observe at this equation, which is to be differentiated with respect to voltage. Let us see which are varying or which are not varying with respect to voltage. Which voltage? Reverse voltage. Q is charge. It will not vary with reverse voltage. Nd, donor concentration. It will not vary with voltage. Area of cross section of diode will not vary with reverse voltage. But as reverse voltage varies, width of depletion region will vary. If reverse bias is increased, it will increase. And hence, AQ and D are constants. So this is written as dW by dVj. Now, we already have an equation for Vj as Q and D W square by 2 epsilon. What is Vj? Junction voltage. Now I am differentiating this with respect to Vj. Now again Q Nd 2 epsilon will be constant. This W square will become 2W into dW by dVj. If 2 is cancelled out, then let us see what we get. dVj by dVj is 1. So from this dW by dVj comes out as epsilon by Q and D into W. Now this value of dW by dVj, which has been just now derived by differentiating junction voltage equation, will be substituted into this place of Ct transition capacitance equation. Cancel out the common terms. Then we are left with Ct equal to epsilon A by W. So this is the final equation for transition capacitance, where epsilon is permittivity, A area of cross section, and W is width of depletion region. And this transition capacitance equation is very much important. It has been asked multiple times in university examination. Let me see whether there are any queries from the end of students. Okay, we'll continue the discussion. Change in reverse bias changes width of depletion region. Hence, it can be used as voltage variable capacitor. Suppose reverse bias is increased, then width of depletion region will increase, and hence transition capacitance will decrease, or vice versa. That is, if reverse bias is decreased, width of depletion region decreases, transition capacitance increases. Why? Because these two are constant with respect to reverse bias. So by changing voltage, we can vary transition capacitance, and hence a PN diode can be used as voltage variable capacitor. This is one of the applications of PN diode. See, I am discussing this concept. Why? Because plenty of times a short answer question was asked. That is, comment on voltage variable capacitor, or draw the voltage variable capacitor characteristics for a PN diode, which is a short answer question, maybe asked for 3 marks or 4 marks, which has been repeatedly asked. So for 3 mark or 4 mark question, no need of doing the derivation of transition capacitance. Only comment on how transition capacitance varies with respect to reverse voltage. Now, these are the different names for this voltage variable capacitor. It can be observed very easily as how we got these names. VOLTA, volta of voltage, CAP of capacitor. Put together, we get the name volta cap. Similarly, VOLTA of voltage, VARI of varicap of variable, and CAP of capacitor. Put together, we get the name varicap. Or it is also given the name varactor diode. Remember that names will also have a particular meaning. So varicap means variable capacitor. Volta cap means a capacitance which will vary with voltage. These are the different names. And this is the circuit symbol. It can be easily observed that the circuit symbol has been derived from the circuit symbols of PN diode and capacitance. This is the circuit symbol of a PN diode. And this is the circuit symbol of a capacitance. As we know, this arrow shows variable. If we merge these two circuit symbols, we get this. So even circuit symbols have an internal meaning. Based on that, you can easily remember. And this is the equivalent circuit, wherein we are showing a variable transition capacitance. This occurs only in reverse bias. Remember that this transition capacitance which we are commenting is existing only in reverse bias. This graph is drawn for transition capacitance expressed in PF, picofarads, 10 to the power of minus 12 farads versus reverse voltage. This is minus 5 volts, this is minus 10 volts, this is minus 15 volts. As we know, as reverse voltage increases, width of depletion region increases. Denominator is increasing and hence transition capacitance decreases. That's what we observe. This pink color line shows capacitance decreases as reverse voltage increases. This is the characteristics of PN diode when it is being used as VariCap, that is variable capacitor or varactor diode. This is what I said has been repeatedly asked for a short answer question. There are multiple applications for varactor diode. It can be used as voltage controlled oscillator. It can be used as frequency modulator. It can be used in tank circuits, automatic frequency control, AFC, and also frequency multiplier. Okay. This completes the discussion of derivation of transition capacitance and one of the applications of PN diode, that is voltage variable capacitor, and its concerned graph. Before moving on to the next derivation, that is diode resistances, let me see whether any queries has been raised by the students. Okay. Now, this is one more important topic which has been repeatedly asked in the university examination. As we know, the main idea of this videos is to give answers for very important questions with respect to university examination. Plenty of times in the university examination, diode resistances and numerical based on diode resistances will be asked. Let us see as what it is. Every material in this world will exhibit a resistance. If it is conductor, resistance is low. If it is insulator, resistance is high, very high. If it is semiconductor, it is medium. So every material in this world will exhibit a resistance. PN diode is made up of either silicon or germanium. So it also exhibits some resistance. But in PN diode, resistance will vary, depends on the state of diode, whether it is forward biased or reverse biased. So depending on bias, width of depletion region will vary and hence resistance of diode will also vary. Let us see why the resistance will vary based on width of depletion region or based on bias. Now, if you can look at this diagram, this red color circles are free electrons, white color circles are holes. Positive means positively charged donor ion. Negative means negatively charged acceptor ion. In N side of diode, electrons are majority carriers, holes are minority carriers, and hence we see less number of holes are existing. In P side, holes are majority carriers, electrons are minority carriers, and hence we see few electrons are existing. As long as electrons and holes are existing, support of current could be possible. But in this central part, which is called as barrier or depletion region or space charge region or junction, we have positive and negative ions, also called as immobile ions, which cannot support current, So, in a forward bias diode, if you can observe here, to the P side, positive supply is given, to the N side, negative supply is given, and hence the diode is under forward bias condition. In a forward bias diode, width of depletion region is narrow, and hence number of immobile ions are also less, and hence resistance will also be less. Now consider a reverse bias diode. It can be observed that to the N side positive supply is given, to the P side negative supply is given, and hence the diode is under reverse bias condition. In a reverse bias diode, charge carriers are pulled away to the left or to the right, are pulled away from the central area, and hence more number of immobile ions will get created. You can observe there, number of positive ions or number of negative ions are more. These positive ions got created from donor atoms. These negative ions got created from acceptor atoms. Since this depletion region is having more ions or less number of charge carriers, resistance will be high. So, in a PN diode, resistance depends on bias. In forward bias, width of depletion region is narrow and hence resistance is low. Ideally 0, practically low. In a reverse bias diode, width of depletion region is high and hence resistance is high, practically of the order of mega ohms. Ideally it is infinity. Now we move on to the derivation of this resistance of the PN diode. Q stands for operating point. This is the characteristics of a PN diode. VD is voltage across diode, shown on x-axis. ID is current through diode, shown on y-axis. Until V gamma cut-in voltage or offset voltage or breakpoint voltage or threshold voltage or firing point voltage, current will be very small for practical case, 0 for ideal case. Beyond V gamma, as forward bias increases, current increases. How? Exponentially. Now, at the operating point, drop a perpendicular and draw a horizontal and find out voltage and current. Take the ratio of it. It is defined as static resistance or DC resistance. V by I, the unit of resistance will be ohms. Here a small problem is existing. As the location of operating point varies, static resistance will also vary. Why? Because this is exponential in nature. Current in a forward bias diode increases exponentially. So, as the location of operating point varies, DC or static resistance will also vary. To get rid of this problem, we define one more resistance called AC or dynamic resistance. So, as operating point varies, resistance will also vary. So, we are defining one more resistance by name dynamic resistance. Capital R generally stands for static resistance, small r generally stands for dynamic resistance. That is, at the operating point, draw a tangent. Draw a tangent to the characteristics. Find out the slope tan phi. Find out the slope tan phi. Then inverse of slope is defined as RAC, dV by di. So 1 over tan phi is dV by di or RAC. Now we will move on to the equation, RAC equation. Derivation of dynamic resistance equation. Now we will look at that particular thing. Here, this is the equation for current flowing through a diode, and this is the circuit symbol and current and voltage of a diode. With respect to this equation and this circuit symbol, some nomenclature is to be explained here. Consider a simple circuit diagram having a PN diode in parallel with a resistance R1 followed by a series resistance R2, to which some 5 volts supply is given, and in the circuit 10 milliamps of current is flowing. Now let us see as what is the meaning of I. What is the meaning of I? I is defined as current flowing through the diode from P to N. This is what is called as I. By looking at this circuit diagram, can we say that I is equal to 10 milliamps or I is less than 10 milliamps? It can be clearly observed that this 10 milliamps of current is entering and a part of it is going through diode and a part of it is going through R1. That is, current through diode is not 10 milliamps. It is definitely less than 10 milliamps. So remember one important thing, that in this equation I is not current flowing through the circuit. I is not current flowing through the circuit. It is current flowing through the diode from P to N. From P to N. If current is going from N to P, if current is going from N to P, then I is negative. I is negative. If I is positive, diode is forward biased. If I is negative, diode is reverse biased. I naught is called reverse saturation current, and V is defined as voltage across terminals of diode with positive at P side. So this is how V has been defined. By looking at this circuit, it can be easily understood that V is not equal to 5 volts or V is less than 5 volts. Why? Because this resistance will take some drop. So remember one important thing, that in this equation V is not the voltage applied to the circuit. V is not the voltage applied to the circuit. V is voltage across terminals of diode. V is voltage across terminals of diode that too positive at P side, that too positive at P side. I'll do a simple modification to this circuit. Assume the supply polarities are inverted. The supply polarities are inverted. Then do not change polarities of V. Instead make V negative. Instead make V negative. Remember that if V is positive in this equation, then the diode is forward biased. If V is negative, then the diode is reverse biased. I am specifically defining the meaning of I and V. Why? Because based on how you understand the meaning of I and V, solving a numerical will become easy. Eta is a constant and Vt is thermal equivalent voltage, which is T degrees Kelvin by 11,600. We have something called as instance relationship. From that we got the value of this Vt. Default temperature, room temperature is 300 Kelvin. If you substitute 300 Kelvin here, Vt comes out as 0.026. This value of Vt at room temperature, that is 27 centigrade or 300 Kelvin, should be definitely remembered. It is useful in most of the numericals. There are certain standard values to be remembered while solving numericals, and one of them is Vt, especially while calculating the current or voltage of a PN diode. This value is to be remembered. Now, until now we have defined as what is the meaning of I, what is the meaning of I naught, what is the meaning of V, etc. Now we move back to the dynamic resistance derivation. We want to differentiate this current with respect to voltage. As we know, this I naught is reverse saturation current. It depends only on temperature. It does not depend on the voltage. Reverse voltage may increase or decrease. Still I naught will be constant. I naught is dependent on temperature. Here I want to add one more comment. For every 10 degrees centigrade rise in temperature, I naught gets doubled. That is, for every 10 degrees centigrade rise in temperature, I naught gets doubled. That is to be remembered. As we know, I naught reverse saturation current is dependent on minority carriers. As temperature increases, electron hole pair generation increases. So minority carriers increases and hence reverse current also increases. So this I naught is a constant, it is pulled out. D by dV of e to the power of V by eta Vt will come out as e to the power of V by eta Vt into 1 by e to the power of 1 by eta into Vt into dV by dV, where dV by dV is 1. And this is a constant. Derivative of constant will come out as 0. So that's what I said earlier. I naught, eta and Vt are independent of applied voltage. This is independent of applied voltage. This is also independent of applied voltage. Only this becomes dV by dV as 1. We have got the equation for di by dV, but the dynamic resistance by definition is dV by di. So we should invert this equation. Then we get this. So equation for dynamic resistance is eta Vt by I naught into e to the power of V by eta Vt. Important thing to be remembered here is V is positive for a forward biased diode and V is negative for a reverse biased diode. So this is to be remembered especially while solving numericals. This eta depends on germanium or silicon. Vt depends on room temperature. I naught is a constant value for a given diode. If you reorganize the terms of this equation, I naught into e to the power of V by eta Vt comes out as I plus I naught. Now, in this I naught into e to the power of V by eta Vt is going to get replaced by I plus I naught. This is also a valid equation for dynamic resistance of a PN diode. See, which equation is to be used while solving numericals depend on the data supplied. Suppose in a diode, current through diode and I naught is given. You are asked to find out dynamic resistance, then use this equation, because eta depends on germanium or silicon diode, Vt depends on temperature, and I and I naught are already supplied. Suppose in a problem statement, I naught and voltage, either reverse bias or forward bias is given, then use this equation. Remember that both equations are valid. Which equation is to be used depends on as what data is supplied in the problem statement. In a forward bias diode, I is very much greater than I naught, because I is of the order of milliamps or amps in a forward bias diode. I naught, as we know, is a very small value. It is microamps for germanium, nanoamps for silicon. So if at all we want to find out dynamic resistance of a forward bias diode, then compare it to I naught can be neglected, and hence equation gets modified as eta Vt by I. Remember one important thing, that this equation is valid only for forward bias diode. Don't use it for reverse bias. Okay. Dynamic conductance by definition is 1 over dynamic resistance. This completes the derivation of static and dynamic resistance of a PN diode. This is also a very, very important question. It has been repeatedly asked in the university examination for about 4 marks or 6 marks. Let me see whether any doubts has been expressed by the students. There are no more doubts, so I'll continue the discussion. We'll just solve a numerical and close this session. And before that, let me see one of the major application of a PN diode, that is switch. As we know that in forward bias, a PN diode can be used like an on switch, whereas in reverse bias, a PN diode can be used like an off switch. We'll just comment on this and then go on to a numerical and then close the session. Now, just now we stated that in a forward bias diode, width of depletion region is very less, and hence resistance will also be less. It is of the order of few ohms in a practical case and 0 in an ideal case. Resistance is 0 means current is infinity. If resistance is low, current is maximum, milliamps or amps. So a PN diode can be used like an on switch in forward bias condition, which is called as short circuit. Now, in a reverse bias diode, width of depletion region is high, and hence resistance is large, mega ohms. Mega means 10 power 6. And ideally it is infinity. Ideally it is infinity. If resistance is infinity for ideal case, then current should be 0. If resistance is maximum, current will be minimum. Microamps 10 power minus 6 or nanoamps 10 power minus 9. So now, in a reverse bias case, a p-end can be used like off switch. Ideal case, open circuit, but generally off switch. So a p-n diode can be used as switch. Now, let us see the different applications of a p-n diode. It can be used as switch, just now explained. It can be used as rectifier, clipper, clamper, logic gate, sampling gate, comparator, and variable capacitor. Remember that in all these applications, except the last one, p-n diode is being used as switch only. In rectifier, p-n diode is used like switch. In clipper, p-n diode is used like switch. In clamper, also p-n diode is used like switch. Ideally speaking, p-n diode has two major applications, that is switch and variable capacitor. But in switch, there are multiple applications as given earlier. Now we move on to the numerical related to dynamic resistance of a p-n diode. Before going to the numerical, first of all, I'll give you a procedure or steps to solve a numerical. Here, to all the students, I want to give one important suggestion. Remember that if you want to get maximum marks for a question in the university examination, the best way is to attempt a numerical. Because in numerical, if you write all the steps and do substitution and give the correct answer along with units, you will get full marks. Whereas if you choose a theory question, irrespective of how much amount of theory you write, the examiner may not get satisfied and hence you may not get full marks. So if you want to get full marks, first preference is to choose a numerical. Second preference is choose a question in which there is a derivation, like just now we have derived transition capacitance, or choose a question in which voluminous diagrams are existing. For example, if you take tunnel diode operation, voluminous energy diagrams will be existing. Once all diagrams are drawn perfectly, there is a probability of getting more number of marks. And one more advantage in choosing a numerical is in less time you can get maximum marks. Maybe you will write 4 steps or 5 steps or 8 steps, but you will be able to get 5 marks. If you choose a theory question, even if you write 30 lines or 40 lines, you may not get full marks because examiner may feel some small data is missing. If you want to get full marks for a numerical, certain procedures or certain steps are to be followed. And that is what is given here. Let me see at it one by one. First of all, given data, it is very simple. Copy the data given in the problem statement into the answer sheet below the heading solution. Next one is required data. That is what is supposed to be calculated. Next one, assumptions if any. Remember that for a numerical, certain assumptions could be required. For example, suppose in a numerical temperature is not given and you want to substitute a value for Vt, which is equal to T degrees Kelvin by 11,600. The temperature is not given, so it can be assumed as default 27 degrees centigrade or 300 Kelvin, that is the room temperature. So that can be written there. And sometimes a note may also be required. Suppose in a problem statement a value is not supplied, or say as said earlier, you are asked to find out by how much amount I naught reverse saturation current increases. If temperature increases, say from 25 degrees centigrade to 55 degrees centigrade, and no data is supplied further, then what you can do is, in note you can put in this way. It is assumed that I naught reverse saturation current will get doubled for every 10 degrees centigrade rise in temperature, and based on that you can solve the numerical, because that is the default rise in I naught. If a value is given, use the value. If nothing is given, write a note and use it. Later on, write the equation whichever is required to solve the numerical, and then do the substitutions and simplification. Remember that this is very important. Most of the students will do a mistake of this nature. That is, this substitution and simplification they will do on the question paper or somewhere in the back page with the heading rough sheet, and directly write the value in the main place. Then the examiner may assume that you have copied the answer or you wrote some random answer based on some estimation. It is better to do the substitution and simplification steps at the regular place only, so that examiner will be satisfied that you have done on your own. Later on, write the answer along with the units, and better put a box over it. Suppose you are asked to find out some dynamic resistance of a diode. At the end you can say R equal to, say, some 20 ohms. Put a box on that. If possible, write ANS answer beside it also. If you write in this fashion, examiner can easily verify as where the answer is located. If you follow these steps, I am very sure you will get full marks in minimum time. Now I am taking a simple numerical for a germanium diode operating at 100 degrees centigrade. Reverse saturation current is 20 microamps. Calculate dynamic resistance for a bias of V equal to 0.1 volts, and part B, V equal to minus 0.1 volts. V equal to 0.1 means the diode is forward biased. V equal to minus 0.1 means the diode is reverse biased. He is asking us to find out what dynamic resistance. Now, on par with the steps or procedure given earlier, I'll solve the numerical. First thing, put the subheading solution, later on given data. He is commenting on a germanium diode. As we know, for a germanium diode, eta equal to 1. And he is commenting on temperature of 100 degrees centigrade. It is better to convert temperature to Kelvin, because in dynamic resistance equation, Vt is given in terms of Kelvin. Remember that if temperature is not given in a problem statement, we can assume it as 27 degrees centigrade or 300 Kelvin. But in this problem, he has specifically given it as 100 degree centigrade. Next, reverse saturation current is 20 microamps. Remember that I naught is given as 20 microamps. In the given data, write the name of variable also. We are assuming eta as 1 and I naught is 20 microamps. So that while doing substitution, it becomes easy for you. Next step is required data. He is asking us to find out dynamic resistance for part A and part B. And there are no assumptions here. You need not write assumption is nil. Even if you write, there is no problem with that. And here I am writing a note. Temperature is given as 373 degree Kelvin. Equation for Vt is T degrees Kelvin by 11,600 Substitute this temperature here and simplify. Now you will recall as why I am putting it as a note. I already stated that default value of Vt is 0.026 at 300 Kelvin, which is to be used in any numerical if temperature is not supplied. But in this problem statement, temperature is specifically given as 373 Kelvin or 100 degrees centigrade. So we cannot use the default value of Vt, and hence I have recalculated Vt based on the regular equation. And this is the crux of the problem. This is the crux of the problem. Most of the students unknowingly will substitute 0.026 and get an answer and come out of the examination hall assuming that what they wrote is correct. But this is very, very important to be remembered. So whenever you are solving a problem, I suggest that observe as what is given in the problem statement, then only solve it. Now, we have the equation for dynamic resistance as eta Vt by I naught into e to the power of V by eta Vt. And all values are already given. Eta is 1, which we got from problem statement. Vt is 0.032, which we have found, which was explained in the note. I naught is given as 20 microamps in the problem statement. And there are two parts. Part A, V plus 0.1, part B, V minus 0.1. Here, as I said earlier, substitutions are required. I'll just write in a simple fashion here. I naught is how much? 20 microamps. E to the power of V by eta Vt. Assume part A, V is 0.1. And eta is 1. Et is 0.032. And numerator we have 1 into 0.032. This is what I have said to be done as substitution. Few students, what they do is, they'll substitute these things directly into the calculator and write the answer here. Don't do that. Write steps of this nature. If possible, write one more step, that is, find out the value of exponent. Write another step. And write another step to write the value of denominator. Write 3 or 4 steps and then give the final answer. While giving the final answer, first of all write the name of variable, put equality sign, put the value followed by unit, and then if possible put a box over it and write ANS like that. Now this is the value of resistance, dynamic resistance for V equal to minus 0.1, that is in kilo ohms. This is the value of resistance for V equal to plus 0.1 forward bias. This is in ohms. So as I said earlier, for a forward bias diode, width of depletion region is less, hence resistance is low. Whereas for a reverse bias diode, width of depletion region is high, hence resistance is high. I suggest all the students to verify whether your answer is matching with this statement or not. Suppose in a reverse bias diode, you are not getting a large resistance of the order of kilo ohms or mega ohms. Remember that you would have forgotten to substitute the negative sign. See, in few numericals, after you got the answer, you can verify at least whether the got answer is correct or wrong. So, if you do not get less resistance in forward bias, if you do not get large resistance in reverse bias, please check whether you have done any mistake at any point. Let me see whether any queries has been asked. Okay. There are no more queries asked in this. I assume that this information is very helpful for you for writing the university examination. There are multiple topics in a PN diode. I have chosen to comment on the derivation of transition capacitance, which is a repeatedly asked question, derivation of resistance of PN diode, and solved a numerical based on that. I thank you all the students for watching the video. Thank you.